So now we want to apply the advection schemes. And what we want to do is we want to simulate the flow around obstacles, so-called island wave. And there's a little sketch here, and there is a 3 parameters that determine the dynamics of the flow around an obstacle. So consider that you have a solid cylinder, and the scale of that is L, is the diameter of this object. And you have a flow coming from the left, and the speed of this flow is u. And in addition to that, we have a viscosity, a viscosity effect characterizing the fluid that you're using. The viscosity keeps the flow close to the cylinder. Okay, so shown here is a situation of a smooth flow just moving around. So now you can formulate something that we call a non-dimensional number based on these 3 parameters. That is called the Reynolds number. The Reynolds number is U times L divided by the nu, which is the kinematic viscosity. And now, dependent on the magnitude of the Reynolds number, you get different dynamics, and they are shown here on the next. Look, different dynamics, and start from top to bottom, and representing increase in the Reynolds. The Reynolds number is very low. You get a smooth flow, a so-called laminar boundary layer, laminar flow. Okay? And essentially, we look from above here and there. Okay, no separation, laminar boundary layer, just smooth flow that goes around your obstacle. Doesn't do it. If you then increase the Reynolds number, you can increase the Reynolds number by different effects. You use a different fluid with a different viscosity, or you increase the flow speed, or you change the size of your. All right. Anyway, so if you have a higher Reynolds number, what you get is a feature that we call a return flow. There's a return flow. And you get something that we call a vortex. You get actually 2 vortex pair elements that recirculate material. So then if you further increase the Reynolds number, you get something we call a turbulent wake. And then in the most extreme case, you actually get something that we call a Van Karman vortex. It's a beautiful pattern that you can visualize in experiments if you use, for smoke. You can visualize it. I want to show you an example. This is one example, and I have to move myself away. This, hang on. See whether some manage. Now I can move myself. And this is how it looks like. Here's your object. Sorry. Here's your object. You have the flow, and then you get a pattern that looks like a yin and yang pattern, swirling smoke. Yep. So this is what we want to simulate. This is what we want to simulate with our. Do you think we managed that with our 2-dimensional model? Let's see. Let's have a look. Let's have a go at that.